What if everything you see around you, the stars, the planets, even the room you're sitting in, is just a tiny fraction of reality? What if there are hidden layers of existence, dimensions beyond our perception, curled up so tightly or stretched so far that we can't even begin to fathom them? The universe has always been full of mysteries, but few are as tantalizing as the idea that there might be more to reality than the three dimensions we experience every day. Scientists and thinkers have spent centuries wrestling with this possibility, and what they've discovered will bend your understanding of space, time, and the very fabric of existence. Think about the last time you looked up at the night sky. The vastness of space feels infinite, doesn't it? But here's the mind-blowing part. What if that infinity is just the surface? What if, hidden within the fabric of the cosmos, there are extra dimensions, unseen realms that hold the keys to mysteries like dark matter, gravity, and even the birth of the universe itself? From the wild predictions of string theory to the mind-bending mathematics of higher dimensional physics, researchers have proposed theories so strange they sound like science fiction, except they might just be science fact. That's exactly what we're diving into today. We're about to explore 30 of the most fascinating, jaw-dropping theories about the universe's hidden dimensions. Some of these ideas will challenge everything you thought you knew. Others might make you question whether we're alone in the cosmos or if something unimaginable is lurking just beyond our sight. So buckle up, because this journey isn't just about learning. It's about stepping into the unknown, where the rules of reality as we know them might not apply. Are you ready to see what's really out there? Let's begin. One of the most revolutionary ideas in modern physics is string theory, a framework that suggests particles aren't just tiny dots, they're actually vibrating strings. But here's where it gets weird. For these strings to make sense mathematically, they can't just exist in the three dimensions we're familiar with. Instead, string theory demands there are at least 10 dimensions, maybe even 11, all woven into the fabric of reality. So where are they? Imagine a spiderweb glistening in the morning dew. From a distance it looks flat, two-dimensional, but up close you see intricate layers, threads intersecting in ways you couldn't perceive before. Extra dimensions might be like that, curled up so tightly or stretched so thin that our senses and instruments haven't detected them yet. Why would nature need these hidden dimensions? Think of it like a musical instrument. A guitar string can vibrate in different ways, producing distinct notes. Similarly, the way strings vibrate in higher dimensions could determine everything from the mass of an electron to the strength of gravity. This could be the missing puzzle piece that unites quantum mechanics, which governs the smallest particles, with Einstein's theory of general relativity, which explains the cosmos on a massive scale. Right now, these two theories don't play nicely together, but if extra dimensions exist, they might be the common language both have been searching for. Some physicists argue these dimensions aren't just mathematical quirks. They could be the reason gravity feels so weak compared to other forces. While electromagnetism holds atoms together with ease, gravity barely keeps your feet on the ground. What if gravity isn't weak at all? What if it's just leaking into other dimensions, diluting its strength in our observable universe? It's a startling thought, one that could rewrite our understanding of everything from black holes to the Big Bang. String theory isn't just about hidden dimensions, it's about redefining reality itself. And the craziest part, we might be standing on the edge of proving it. Now picture our entire universe not as an isolated expanse, but as a single sheet of paper floating inside a vast multidimensional library. This is the Brane World scenario, one of the most radical twists on hidden dimensions. According to this theory, what we call home might just be a three-dimensional brane, short for membrane, adrift in a higher dimensional space called the bulk. Imagine ants crawling across the surface of that sheet of paper, completely unaware of the shelves towering above them. To us, those shelves could be dimensions beyond our perception, realms where the fundamental rules of reality might be completely different. So why would our universe be stuck on a brane? Think of gravity as the key clue. Unlike other forces like electromagnetism, which stay tightly bound to our brain, gravity might have the unique ability to leak into the bulk. Picture a sponge soaking up water. Some liquid stays trapped inside, but some seeps through to the other side. If gravity behaves similarly, that could explain why it feels so feeble in our everyday lives. While a magnet can lift a paperclip with ease, Earth's entire mass barely keeps us from floating away. The Brane World idea suggests gravity isn't weak, it's just spreading its influence across dimensions we can't see. But here's where it gets even wilder. If our brain exists within this cosmic bulk, there could be countless parallel universes drifting just out of reach. Picture bubbles in a glass of soda, each one a self-contained reality with its own stars, planets, and maybe even versions of you. Collisions between these branes might even trigger cosmic cataclysms like the Big Bang itself. Some researchers speculate our universe wasn't born from a singularity, but from two branes smashing together in the bulk, unleashing energy that became everything we know. The craziest part, we might actually test this. The Large Hadron Collider, the most powerful particle accelerator ever built, could uncover hints of these extra dimensions. How? By searching for microscopic black holes, tiny gravitational whirlpools that might form if high-energy collisions punch through our brain into the bulk. Or by detecting gravitons, hypothetical particles that carry gravity, which could briefly vanish into higher dimensions before reappearing. It's like throwing a ball against a wall and watching it mysteriously lose energy, as if some of it slipped into another room. Whether the Brane World scenario holds up or not, it forces us to rethink our place in the cosmos. We might not be the center of existence, just residents of one page in a multidimensional book we're only beginning to read. And if other branes are out there, who's to say what or who might be living on them? Long before string theory or Brane worlds, two brilliant minds dared to suggest something radical. What if Einstein's theory of gravity was missing a piece? In 1921, mathematician Theodore Kaluza sent a letter to Albert Einstein with an astonishing idea. What if we live in a universe with not just 4 dimensions, 3 of space and 1 of time, but 5? Kaluza showed that by adding this unseen dimension, the equations of general relativity could also describe electromagnetism, unifying 2 fundamental forces under one elegant framework. At first, Einstein was skeptical. The concept seemed too beautiful to be true, but the math held up, revealing a hidden symmetry between forces that had always appeared separate. Here's how it works. Imagine a garden hose stretching far into the distance. From far away, it looks like a simple line, one-dimensional. But up close, you realize it's actually a cylinder with a circular dimension curled up so tightly you'd need microscopic eyes to see it. Kaluza and later physicist Oscar Klein proposed that the universe might work the same way. The 5th dimension could be curled into a loop smaller than an atom, explaining why we don't notice it in daily life. Every point in our familiar 4-dimensional spacetime might secretly hide this tiny, coiled ring, a dimension influencing reality in ways we're only beginning to grasp. Klein took the idea further, suggesting particles like electrons might actually be waves traveling in this hidden dimension. Just as plucking a guitar string produces musical notes, vibrations in the 5th dimension could generate different particles. A low-frequency vibration might appear as an electron, while a higher one could become a photon, the particle of light. This groundbreaking insight laid the foundation for modern theories of extra dimensions, showing how unseen geometry might dictate the laws of physics. Yet for decades, the Kaluza-Klein theory faced a major hurdle. If this 5th dimension existed, where were its effects? Why couldn't we detect it? The answer lies in scale. These dimensions might be curled up at distances a billion times smaller than an atom. far beyond the reach of even today's most powerful microscopes. But their influence could still echo across the cosmos. Some physicists speculate that if we could probe these unimaginably tiny distances, we might find particles with Kaluza-Klein modes, heavy cousins of familiar particles, carrying the imprint of higher dimensional vibrations. What's remarkable is how ahead of their time Kaluza and Klein were. Their work, once seen as a mathematical curiosity, now fuels cutting-edge research. The Large Hadron Collider has searched for those heavy particle echoes, and theories like string theory owe a debt to their pioneering vision. They taught us that dimensions might not just stretch outward into space. They could be hidden in plain sight, woven into the fabric of reality itself. And if they were right, the universe is far more intricate and far more interconnected than we ever dreamed. Now imagine trying to fold an entire dimension into a space so small. It's like shrinking an ocean into a droplet. That's the puzzle physicists faced when searching for how extra dimensions could hide. Enter Calabi-Yau manifolds, the geometric masterpieces that might hold the answer. These bizarre, six-dimensional shapes are the hidden architects of string theory's extra dimensions, twisting space into forms so intricate they resemble alien origami. Picture a snowflake's delicate symmetry, but amplified into a multidimensional labyrinth where every curve and fold could dictate the laws of our universe. Why 6 dimensions? Think of it like tuning a radio. Each twist in a Calabi-Yau shape affects how strings vibrate within it, influencing the particles those vibrations create. One configuration might produce electrons, another quarks, like adjusting microscopic dials to generate different cosmic building blocks. These manifolds don't just hide dimensions, they're cosmic choreographers, directing the dance of matter and energy at the smallest scales. But here's the twist, there isn't just one Calabi-Yau shape. Mathematicians have discovered tens of thousands of possible configurations, each potentially birthing a universe with entirely different physics. It's as if nature handed us a catalogue of possible realities, and we're stuck on page 1. Some of these shapes might allow for stable atoms and galaxies, while others could render life impossible. A dizzying landscape of potential universes where ours is just one tiny island of habitability. The real magic lies in how these manifolds compactify dimensions. Picture a garden hose again, but this time it's woven into a hyper-dimensional knot. From afar, it looks smooth and simple, but up close, its complex structure governs everything. In string theory, particles aren't just points, they're loops vibrating through all 10 dimensions, with their properties determined by how they navigate these folded geometries. A string threading tightly around a curled-up dimension might emerge as a heavy particle, while one gliding loosely could be massless like a photon. Critics argue this sounds like mathematical fantasy, but Calabi-Yau manifolds aren't just pretty equations. They've appeared unexpectedly in real-world physics, like their role in mirror symmetry, a deep connection between seemingly unrelated string theories that stunned researchers. It's as if the universe left breadcrumbs in pure math, hinting that these shapes are more than fiction. The stakes couldn't be higher. If Calabi-Yau manifolds are real, they'd answer why our universe has the exact mix of forces and particles it does, and suggest countless others might exist with different rules. It's a humbling thought. The fabric of reality might hinge on geometries so complex we're still learning to see them. What if every person, planet, and galaxy we see is nothing more than an illusion, a three-dimensional movie projected from information scribbled on a flat cosmic canvas? This is the essence of the holographic principle, one of the most unsettling ideas in modern physics. It suggests that our entire universe might operate like an incredibly detailed hologram, where all the depth, texture, and complexity we perceive is actually encoded on a distant two-dimensional surface we'll never see. The concept sounds like science fiction, but it emerges from some of the most rigorous studies of black holes and quantum gravity. Take a black hole's event horizon, the point of no return for anything that gets too close. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized a black hole's entropy, a measure of disorder, isn't determined by its volume, as you'd expect for a three-dimensional object. Instead, it's proportional to the area of its event horizon, that two-dimensional boundary. It was as if all the information about what fell into the black hole wasn't lost inside but smeared across its surface like cosmic graffiti. Decades later, string theorist Leonard Susskind and Nobel laureate Gerard T. Hooft took this further, proposing that the entire universe might follow the same rule. Every particle, every force, every ripple of energy in our three-dimensional world could just be shadows cast by quantum data written on some unimaginably vast flat boundary at the edge of space-time. This idea found concrete form in something called the AD-S/CFT correspondence, a mathematical bridge between two seemingly unrelated theories. On one side, you have a 10-dimensional string theory playing out in a warped space called anti-de Sitter space, abbreviated as AD-S. On the other, a quantum field theory without gravity, living on that space's lower dimensional boundary. The revelation: these theories are equivalent. A universe with gravity can be perfectly described by a gravity-free theory operating on its outer shell. Imagine a snow globe where the swirling flakes inside are entirely defined by patterns etched on its glass surface. Remove the globe, and the equations governing those flat markings still capture everything happening within. Now here's where it bends reality. If the holographic principle holds, your sense of touch, the warmth of sunlight, even the vast gulfs between stars, none of it is fundamentally real in the way we assume. Like the pixels on a screen creating the illusion of depth, we might be experiencing a spectacularly convincing projection. Some researchers speculate this could explain quantum entanglement, the eerie phenomenon where particles instantly influence each other across vast distances. If their connection exists on that deeper two-dimensional layer, what looks like spooky action to us might be plain old cause and effect written in a dimension we can't access. The implications are staggering. It challenges our most basic intuitions about space and existence. Are we living inside a simulation? Not exactly. This isn't some computer-generated illusion. The holographic universe would still be as real as anything can be, just built from different foundational threads than we imagined. It also offers a potential path to unifying quantum mechanics and gravity, since the boundary theory seamlessly blends both. And if true, it means every experiment we've ever run, every observation we've made, is just us decoding the universe's flat, hidden source code without realizing it. So next time you gaze at the stars, consider this wild possibility. The constellations burning light years away, the phone in your hand, even the neurons firing in your brain right now, all might just be ultra-high-definition projections from a cosmic flatland we'll never see. Reality, it seems, has been keeping its deepest secrets written in invisible ink at the edges of existence. What if the hidden dimensions of the universe aren't microscopic at all? What if they're big enough to reach out and touch, stretching nearly a millimeter across, lurking just beyond the limits of our everyday perception? This is the daring premise of large extra dimensions, a theory that flips the script on traditional thinking. Instead of curling up at unfathomably tiny scales, these dimensions could exist at sizes we might one day measure with nothing more than finely tuned lab equipment. The implications are staggering because if true, they'd rewrite our understanding of gravity itself. This idea tackles one of physics' most nagging mysteries, the hierarchy problem. Put simply, gravity is inexplicably weak compared to the other fundamental forces. A fridge magnet can defy the gravitational pull of an entire planet with ease. Why? The large extra dimensions theory offers a radical solution. Imagine gravity isn't weak, it's just diluted. While electromagnetism and nuclear forces are confined to our familiar three-dimensional space, gravity might be spreading its influence into these unseen, millimeter-sized dimensions. Picture a drop of ink falling onto a thin paper towel. The stain spreads outward, becoming fainter as it disperses. Gravity could behave the same way, its strength dissipating as it leaks into adjacent dimensions we can't perceive. Testing this required ingenuity. Enter the torsion balance, a device so sensitive it can detect forces 1 billion times weaker than the weight of a snowflake. In groundbreaking experiments, scientists used these instruments to measure gravity's pull between objects separated by tiny gaps, searching for deviations from Newton's famous inverse square law. If extra dimensions exist at macroscopic scales, gravity should grow stronger at distances smaller than their size, like a whisper suddenly becoming a shout when you step into a hidden room. The results, so far, no definitive proof, but the hunt narrowed these potential dimensions down to less than a human hair's width. What makes this theory so compelling is its audacity. Unlike string theory's minuscule curled-up dimensions, large extra dimensions propose a hidden architecture to reality that's almost within reach. They suggest that the fabric of space might have folds and creases we've missed, not because they're too small, but because we never thought to look at the right scale. And if future experiments find even a hint of their existence, it would mean that the universe's greatest secrets aren't buried in distant galaxies or subatomic particles. They're hiding in plain sight, waiting in the quiet spaces between our fingertips. Ever walked through a funhouse and seen your reflection stretch and twist in those curved mirrors? Now imagine reality itself warping that way, not just light, but space and time bending into strange new shapes. This is the startling vision of the Randall-Sundrum models, where hidden dimensions aren't just curled up or flat, they're dramatically distorted by gravity, creating cosmic funhouse effects that could explain some of the universe's deepest mysteries. Picture a bedsheet stretched tight between two poles. Drop a bowling ball in the center, and the fabric sags into a steep valley. That's how gravity warps spacetime, according to Einstein. But Lisa Randall and Ramon Sundrum proposed something wilder. What if entire dimensions bend like that? Their model suggests one of the extra dimensions could be a tightly curved throat of space, with our universe stuck on one end like a speck clinging to the rim of a gravitational whirlpool. Unlike the flat, symmetrical shapes of earlier theories, these dimensions are twisted landscapes where gravity's pull varies wildly from point to point. Here's where it gets brilliant. This warping could act like a cosmic filter, trapping certain particles on our three-dimensional brain while letting others escape. Think of the Higgs boson, the particle that gives others mass. Why is it so heavy compared to, say, photons? In the Randall-Sundrum world, the Higgs might be stuck deep in the gravity well of our brain, like a marble rolling into the lowest point of a bowl. Meanwhile, gravity, carried by hypothetical particles called gravitons, could slip along the warped dimension's steep slopes, leaking into the void beyond. That's why gravity feels feeble to us. Most of its strength is draining away into the cosmic plumbing. This isn't just abstract math. The warped dimension idea solves real puzzles. For one, it neatly sidesteps the hierarchy problem, the baffling gap between gravity's weakness and other forces' strength, without requiring impossibly tiny dimensions. It also hints at how the universe might look near a black hole's event horizon, where dimensions could stretch to breaking point. Even stranger, some versions of the model suggest a shadow brain lurking on the far side of the warped dimension, a parallel universe with its own physics and its own version of you, separated by just a millimeter of twisted space. The beauty of this theory, it's testable. If gravity is leaking into a warped dimension, particle colliders might spot missing energy in high-speed collisions, signs of gravitons slipping into the cosmic folds. Or precision gravity experiments could detect subtle changes in its strength over microscopic distances. Imagine dipping a ruler into water. It appears to bend at the surface because light refracts between air and water. Warped dimensions could create similar illusions, bending the rules of reality in ways we're just learning to measure. So next time you feel gravity's gentle tug, remember, it might not be weak at all. We could be standing at the edge of an invisible vortex, a dimension bent so steeply that most of its power spills into the abyss beyond our perception. The universe, it seems, has been playing funhouse tricks on us all along. The universe ends not with a whimper, but with a crash, an epochal collision between two cosmic sheets in a higher dimensional void. This is the breathtaking premise of the ekpyrotic universe theory, where our Big Bang wasn't a one-time event, but the latest in an endless cycle of brane collisions. Imagine two sheets of paper floating toward each other in a silent, dark room. When they touch, energy erupts along the surface, not with fire, but with the birth of particles, space, and time itself. That's how our universe might have begun, not from a singularity, but from a shattering impact in hidden dimensions we can't see. The ekpyrotic model flips traditional cosmology on its head. Instead of an infinitely dense point exploding outward, it proposes that our three-dimensional brane, the membrane holding our entire observable cosmos, slammed into another parallel brane drifting through the bulk. The force of that collision would have been unimaginable, heating space to trillions of degrees and filling it with searing plasma. Sound familiar? It should. The aftermath would look nearly identical to the classic Big Bang, complete with an expanding universe and a fading afterglow we now detect as the cosmic microwave background. But here's the twist: the cycle doesn't end there. After expanding for billions of years, the branes could pull back together by gravity's invisible thread, setting the stage for another collision, another bang, another universe reborn from the ashes of its predecessor. Why would this matter? For one, it solves a puzzle that stumped cosmologists for decades. Why does our universe look so uniform? The standard Big Bang model requires a mysterious period of hyper-fast inflation to explain why distant regions of space have identical temperatures. But in the ekpyrotic scenario, the branes approach each other slowly over eons, smoothing out wrinkles in space-time long before impact. It's like stretching a crumpled sheet of foil. The act of pulling it taut erases the creases naturally, no cosmic inflation needed. There's even potential evidence hiding in plain sight. The cosmic microwave background, our baby picture of the universe, contains faint swirls and streaks called B modes. Some researchers argue these patterns could be scars from ancient brane collisions, gravitational echoes of the universe's cyclic rebirth. Others suggest they're mere dust in our galaxy. The truth remains uncertain, but future telescopes like the LightBird satellite, set to launch in the 2030s, could settle the debate by mapping these whispers from the dawn of time with unprecedented precision. The implications are staggering. If the ekpyrotic model holds, our universe isn't a one-and-done creation, but a single note in an endless cosmic symphony. Each cycle might last trillions of years, with branes drifting apart and crashing together in a rhythm older than time. It raises haunting questions. How many times has this happened before? Will it happen again? And if so, will the next universe remember us, or will every collision erase the past completely, leaving no trace of the civilizations that came before? Perhaps most mind-bending of all is the idea that the next Big Bang might already be unfolding, not in some distant future, but in a dimension just beyond our perception, where two branes are inching toward their destiny. We're left with a humbling thought. Our entire cosmic history, from the first stars to the thoughts in your brain right now, might just be the fleeting aftermath of a collision we'll never see, and the prelude to one we'll never witness. Two particles separated by vast distances, yet mysteriously linked, change one, and the other reacts instantly, as if no space divides them at all. Einstein famously called this quantum entanglement, spooky action at a distance. But what if the spookiest part isn't the connection itself, but where that connection might be happening? Some physicists suspect entanglement isn't traversing our familiar three-dimensional space, it's taking a shortcut through hidden dimensions, weaving particles together along invisible threads we can't yet detect. Enter the ER equals EPR conjecture, a theory so audacious it ties entanglement to wormholes. Proposed by physicists Juan Maldacena and Leonard Susskind, it suggests that every pair of entangled particles might be connected by a microscopic wormhole, a tunnel through higher dimensional space. Think of it like this: if two friends on opposite sides of a mountain want to whisper secrets, they could shout across the valley, or they could pass a note through a hidden tunnel bored straight through the rock. Entanglement might work the same way, with particles communicating not across the vast gulf of space, but through a folded dimension too tiny to see. Experiments already hint at this eerie possibility. When researchers measure entangled particles, whether they're photons separated by a lab bench or satellites beaming signals across continents, the correlation between their states defies classical physics. No signal could travel fast enough between them to explain the instant synchronization. But if their connection exists outside our dimensions, bypassing ordinary space entirely, the spookiness starts to make sense. It's like two marionettes controlled by the same strings. From the audience's perspective, their movements seem magically coordinated, but the real link exists in the unseen space above the stage. Critics argue this is speculative, and they're right. No one's observed a higher dimensional wormhole yet, but the math is tantalizing. In certain string theory models, entangled particles share quantum information along geometries that resemble folded spacetime. Some simulations even show that creating entanglement between particles could generate these microscopic bridges, as if the universe itself stitches together hidden pathways to preserve the connection. The implications are staggering. If entanglement rides the contours of extra dimensions, it could revolutionize quantum computing, allowing unimaginably fast data to transfer through these cosmic backdoors. It might also explain how black holes preserve information. Their entangled particles could be threading the needle of reality, storing data in dimensions beyond the singularity's reach. And if we could somehow map these invisible pathways, we'd have our first blueprint of the universe's hidden architecture. For now, it remains a breathtaking what if. But in a cosmos where particles whisper to each other across light years, ignoring the rules of space and time, perhaps the most rational explanation is the one that sounds least like science and most like magic. Dark matter is the universe's most frustrating disappearing act. It makes up over 80% of all matter in the cosmos, yet it refuses to interact with light, leaving scientists chasing shadows for decades. But what if we've been looking in the wrong dimensions? Some physicists suspect dark matter isn't just hiding, it's operating in realms beyond our perception, slipping through cracks in reality we can't even see. Think of it like this: imagine a world where everything exists in only 2 dimensions flat, like characters in a comic book. If a 3-dimensional apple suddenly passed through their plane, they wouldn't see the whole fruit. Instead, they'd witness slices appearing and vanishing mysteriously as the apple crossed their dimension. Now flip that idea. Dark matter could be like that apple, particles moving through higher dimensions, only brushing against our 3-dimensional space in ways we can't fully detect. They'd cast gravitational shadows, tugging on galaxies and bending light, while remaining utterly invisible to our telescopes. This theory turns dark matter's elusiveness into a clue. While ordinary particles like electrons and quarks are glued to our dimensional plane, dark matter might be a cosmic wanderer drifting freely through extra dimensions. Gravity, the only force we know reaches across dimensions, could anchor these particles just enough to explain their ghostly influence. It's like feeling the wind tug at your clothes without ever seeing the storm, evidence of something vast moving in spaces beyond our view. The hunt for proof is already underway. Deep underground, where Earth's crust shields detectors from cosmic noise, experiments like Xeno-NNT and LUX Zeppelin are searching for dark matter's faint fingerprints. These machines watch for rare collisions between normal atoms and hypothetical dark particles. But if dark matter is truly slipping between dimensions, it might require even cleverer approaches. like hunting for disturbances in quantum fields that hint at particles leaking in and out of our reality. Critics argue this sounds like a convenient excuse for dark matter's invisibility, but the math holds surprising weight. Certain higher dimensional models predict exactly the gravitational effects we observe in spinning galaxies and colliding galaxy clusters. And if correct, it would mean dark matter isn't an anomaly, it's a signpost pointing toward the universe's hidden architecture, perhaps the most mind-bending implication. If dark matter interacts with extra dimensions, we might be surrounded by entire structures, cosmic mountains, rivers, even civilizations existing just millimeters away in a direction we can't point to. The universe's greatest mystery could be its quietest invitation to look deeper beyond the limits of our dimensional senses. We think of time as a relentless river flowing in one direction, from past to future, but what if that's just an illusion? Einstein shattered our classical view by weaving time into the fabric of spacetime, treating it as the fourth dimension. Yet some physicists suspect even this revolutionary idea might be incomplete. Could time's arrow, its stubborn insistence on moving forward, stem from hidden dimensions tugging at reality behind the scenes? Picture a loaf of sliced bread, where each slice represents the universe at a single moment. In Einstein's block universe model, past, present, and future all exist simultaneously, frozen in the four-dimensional loaf. Your childhood, this exact second, and your distant future are all equally real, just occupying different coordinates in space-time. But here's the twist. This view makes time's flow seem like a cosmic sleight of hand. If all moments exist at once, why do we experience them sequentially? One radical explanation suggests higher dimensions could be the stagehands behind the curtain, creating the illusion of movement. Enter causal dynamical triangulation, a theory that rebuilds space-time from the ground up. Imagine constructing the universe from microscopic Lego blocks, tiny geometric shapes that snap together. At the smallest scales, these blocks fluctuate wildly, with time and space losing their familiar structure. But as you zoom out, something fascinating happens. Just as random water molecules collectively create a flowing stream, these chaotic pieces spontaneously organize into smooth spacetime, with time emerging as a dominant direction. The kicker, this arrow of time might depend on how these building blocks connect across hidden dimensions, like threads passing through a higher dimensional loom. Some models propose time's flow isn't intrinsic but a side effect of our three-dimensional perspective. Think of watching a helicopter spin its blades. From the side, you see clear motion, but look directly down the rotor shaft, and the blades appear frozen. Similarly, our experience of time's passage could be an artifact of how we're oriented within higher dimensional reality. Alternative dimensions might harbor their own arrows of time, flowing in directions we can't perceive. The implications are dizzying. If time emerges from deeper dimensional interactions, it could explain why we remember the past but not the future, a cosmic bias written into the geometry of existence. It might also hint at how black holes scramble time near their edges, or why quantum particles seem to remember their entangled partners. Even more startling, if we could step outside our dimensional frame, we might see time as static as space, a landscape where beginnings and endings are just coordinates waiting to be visited. For now, these ideas hover at the edge of testability. Experiments with quantum gravity probes or ultra-precise atomic clocks might one day reveal traces of time's hidden architecture. Until then, we're left with a haunting possibility. The ticking clock in your room isn't just measuring time, it's echoing the whispers of dimensions beyond our senses. And if that's true, the future isn't ahead of us at all. It's all around us, folded into the hidden creases of reality. Supersymmetry isn't just a fancy idea, it's the universe's ultimate balancing act. Imagine every particle we know, from the humble electron to the elusive neutrino, has a hidden twin. That's the radical promise of supersymmetry, or SUSY for short. These theoretical partner particles aren't just mirror images. They could be the cosmic glue holding hidden dimensions together, weaving the fabric of reality in ways we're only beginning to grasp. Here's how it works. In string theory, those tiny vibrating strings need extra dimensions to dance through, but there's a catch. The math only holds up if these dimensions are curled up perfectly, like a gymnast balancing on a beam. Even the slightest instability and the whole framework collapses. That's where supersymmetry steps in. By assigning every known particle a heavier superpartner, Sussy provides the counterweight needed to stabilize these compactified dimensions. Think of it like building a house on shifting sand. Until you drive deep pilings into solid ground, the structure won't stand. Superpartners are those pilings, anchoring the delicate geometry of hidden dimensions so strings can vibrate without tearing spacetime apart. But Sussy isn't just about neat equations. It could solve real-world mysteries. Take the Higgs boson. Its mass is suspiciously light given the quantum storms raging around it. Without supersymmetry's balancing act, these fluctuations should have blown the Higgs mass to impossibly high values, like a balloon swelling until it pops. Superpartners would cancel out this runaway inflation, acting as cosmic dampers. And here's where it gets wild. If these particles exist, they're not just stabilizing dimensions, they might be signatures of them. Some superpartners could literally be vibrating through higher dimensional space, their properties betraying the unseen folds of reality. That's why the Large Hadron Collider has been hunting them relentlessly. When protons collide at nearly the speed of light, they unleash energies that, if Sussy is real, should briefly conjure superpartners into existence. Scientists scrutinize these collisions for missing energy, telltale gaps in momentum that suggest particles vanishing into extra dimensions. So far, the detectors have stayed quiet, but the search has already reshaped physics. Each unsuccessful scan tightens the noose around possible Sussy models, forcing theorists to rethink how hidden dimensions might be structured. The implications are profound. If supersymmetry is confirmed, it wouldn't just validate superstring theory, it would offer a backstage pass to the universe's hidden architecture. We might finally understand why dimensions curl up the way they do, how gravity tugs across them, and whether other cosmic ballets are playing out in realms beyond our senses. And if Sussy remains elusive, that silence could be just as revealing, hinting that dimensions fold in ways we haven't even dreamed of yet. Either way, the hunt for supersymmetric particles isn't just about finding new pieces of the puzzle, it's about discovering whether the puzzle itself is far bigger than we ever imagined. Imagine a cosmic library so vast, it contains not just every book ever written, but every book that could be written, with different laws of physics in each aisle. This is the staggering vision of string theory's landscape, where 10 to the power of 500 possible vacuum states might each birth an entirely different universe. That number isn't just large, it dwarfs every atom in the observable cosmos, implying a multiverse so diverse, some realities could have 5 dimensions while others have 26, each with its own unique particles, forces, and even versions of time. At the heart of this idea lies string theory's vacuum problem. When physicists tried to calculate how extra dimensions might curl up, they didn't find one tidy solution. They found a jungle of possibilities. Each distinct configuration or vacuum state determines the physics of its universe, like dials on a cosmic control panel. Turn one way and electromagnetism might dominate, twist another, and gravity could be 1,000,000 times stronger. Some configurations permit stars and life, while others collapse instantly or freeze into sterile voids. The real shock, there's no known law favoring one over another, suggesting nature might have rolled the dice countless times. This is where Max Tegmark's classification slices through the debate. His 4-level multiverse framework sorts these ideas from speculative to startlingly plausible. Level 1, a simple extension of cosmic inflation regions so distant their light hasn't reached us yet, but governed by the same physics. Level 2 introduces bubble universes, each with different physical constants born from eternal inflation. String theory's landscape fits here, with Calabi-Yau manifolds acting as cosmic blueprints for each bubble's dimensions. Level 3, the quantum many worlds interpretation, where every decision spawns parallel timelines. But Level 4 is the most radical, a mathematical multiverse where all possible structures exist, including realities with alternate mathematics. String theory's landscape flirts dangerously with this realm, blurring the line between physics and metaphysics. Critics argue this veers into philosophy, not science. After all, if we can't observe these other universes, how can we test their existence? But supporters counter with two compelling points. First, some vacuum states in the string landscape predict our exact universe, its particle masses, force strengths, even the cosmological constant, a striking alignment. Second, cosmic inflation, once deemed untestable, now has observational support. Maybe the multiverse just needs its own smoking gun, like odd patterns in the cosmic microwave background hinting at collisions with other bubbles. The stakes couldn't be higher. If the landscape is real, our universe isn't special, just one garden in a fractal cosmos of possibilities. But if it's wrong, string theory might need a radical rethink. For now, the landscape remains a breathtaking reminder, the answer to why these dimensions might not lie in our universe at all, but in the infinite variations waiting beyond the edge of existence. Black holes have long been cosmic paradoxes, regions where gravity is so intense, not even light can escape. But what if these gravitational monsters aren't just crushing matter into oblivion? What if they're cosmic backdoors, funneling everything that falls in somewhere else, perhaps into other dimensions or parallel branes? This isn't science fiction, it's a serious theory that could solve one of physics' most heated debates, the black hole information paradox. Picture a black hole's event horizon as a one-way membrane. Once matter crosses, it's supposedly lost forever, violating quantum mechanics' rule that information can't be destroyed. This contradiction led to the infamous firewall idea, a hypothetical wall of searing energy at the horizon that burns up infalling matter to preserve information. But firewalls create their own problems, like breaking Einstein's equivalence principle, which says free fall should feel like floating in empty space. Here's where extra dimensions offer an elegant escape hatch. Instead of information frying at the horizon, it might slip into hidden dimensions, like water swirling down a drain, only to emerge in another cosmic sink. String theory adds weight to this idea. Certain models suggest black holes could be bridges, Einstein-Rosen wormholes threading through higher dimensional space. Matter wouldn't pile up at a singularity, it'd traverse the bulk, emerging in another universe or brane. Think of it like a sheet of paper with a hole burned through it. A two-dimensional creature seeing objects vanish into the hole would assume they're gone, but we'd know they just fell into the third dimension. Similarly, a black hole's crush might be our limited perspective of matter exiting our dimensional plane. Even Hawking radiation, the faint glow black holes emit as they evaporate, could carry echoes of this dimensional leakage. If information isn't lost but encoded in higher dimensional geometry, those particles might bear imprints of what fell in, like steam rising from a pot retaining the scent of its ingredients. Experiments aiming to detect subtle quantum correlations in Hawking radiation could one day spot these fingerprints. The implications are staggering. If black holes aren't endpoints but portals, our universe might be part of a vast dimensional network with matter and energy cycling through hidden channels. It's a humbling thought. The darkest objects in space could be the brightest windows into reality's deepest layers, if only we learn to see through them. What if the universe's grandest structures, those vast cosmic webs of galaxies stretching billions of light years, aren't just random scatterings but echoes of hidden dimensional geometry? Zoom out far enough and the universe doesn't look like a smooth soup of matter. Instead, it resembles a sponge, a labyrinth of galaxy filaments twisting around empty voids, a pattern so intricate it defies ordinary dimensions. This cosmic tapestry might not fit neatly into our three-dimensional box. Some researchers argue it exhibits fractional dimensions, a mind-bending middle ground between flat planes and voluminous space, governed by the same mathematical rules as fractals. Fractals are shapes that repeat their patterns at every scale, like a snowflake's branching arms or a coastline's jagged edges. Zoom in or out and the complexity remains. The legendary mathematician Benoit Mandelbrot showed these structures don't have whole number dimensions. A crumpled piece of paper, for instance, might have a dimension of 2.5, more than a flat sheet but less than a solid cube. Now apply that to the cosmos. Galaxy surveys like the Sloan Digital Sky Survey reveal the universe's matter isn't evenly distributed. It clumps into filaments and clusters with gaps so vast they challenge traditional geometry. When scientists analyze these structures, the math points to a fractal dimension around 2.7, closer to a warped surface than the spacious void we assume. How could this happen? One theory suggests the early universe's quantum fluctuations, tiny density ripples in the primordial fireball, might have imprinted fractal-like patterns as space expanded. Gravity then amplified these wrinkles, sculpting them into the cosmic web we see today. It's like blowing up a balloon with ink splatters. The splatters stretch and connect, forming a web-like structure that retains its underlying complexity no matter how much you inflate it. Critics counter that at the largest scales, the universe should smooth out, losing its fractal properties. Yet recent observations keep finding self-similar patterns across mind-boggling distances. Even more intriguing, simulations of dark matter, the invisible scaffolding of the cosmos, produce fractal-like distributions naturally, as if the universe's hidden architecture prefers these twisted blueprints. If true, this rewrites how we perceive reality's fabric. A fractal cosmos wouldn't just be in dimensions, it would be a dimension, a living mathematical artwork where the very concept of size blurs. The next time you gaze at a starry sky, remember, you might not be looking through space but into it, a realm where dimensions fold, twist, and dance in ways we're only beginning to decode. What if the way you perceive reality, the colors, shapes, and sensations flooding your mind right now isn't the full picture, but just a simplified interface your brain creates to navigate the world? Cognitive scientist Donald Hoffman proposes exactly that, an idea that shatters our assumptions about consciousness and reality. His interface theory of perception suggests our senses don't show us truth, they show us what's useful for survival. A desktop computer displays folders and files not because that's how data really looks inside the machine, but because it's a practical way for humans to interact with complexity. Similarly, Hoffman argues, evolution shaped our perceptions to hide reality's intricate machinery behind a user-friendly illusion. Now take this unsettling idea one step further. If our three-dimensional experience is just a crude dashboard, what's running beneath the surface? Some theorists speculate that consciousness itself might be a phenomenon unbound by dimensions, an irreducible aspect of reality that processes spatial dimensions rather than being confined by them. Picture an ant crawling along a telephone wire. To the ant, the wire is its entire world, a one-dimensional path. But we see the truth. The wire snakes through three-dimensional space, looping around poles and tangling with others. Could our own consciousness be like that ant, mistaking its limited perception for the whole of existence while something vast and multidimensional hums beneath? This opens the door to a staggering possibility. Higher dimensional beings might experience forms of consciousness we can't even fathom. While we're stuck perceiving length, width, and depth, a four-dimensional entity could simultaneously observe all sides of an object inside and out without moving. Their thoughts might weave through time like we navigate space, experiencing past and future as fluidly as we stroll down a street. Philosophers call this ultra-consciousness, a mode of awareness so expansive, it makes our richest moments feel like black and white sketches compared to an IMAX universe. The implications ripple across science. Quantum mechanics already hints that observation alters reality. The famous double-slit experiment shows particles behaving differently when watched. If consciousness isn't just a passive receiver but an active participant in dimensional reality, it could explain why the quantum world seems so bizarre to our classical senses. We're like flatlanders trying to comprehend a 3D object. Our tools are too limited to grasp the full picture. Hoffman's theory isn't without critics. Some argue it veers into solipsism, the idea that only the mind is certain to exist. Others counter that evolution would favor accurate perceptions. A lion seen as a harmless blur doesn't bode well for survival, but the math holds surprising weight. Hoffman's models show that perceiving truth isn't always advantageous sometimes. Fitness beats fidelity. A butterfly doesn't need to understand aerodynamics to fly, it just needs wings that work. So next time you gaze at a sunset, consider this wild thought. Those brilliant hues aren't out there in some objective world. They're your brain's best guess at decoding wavelengths, a simplified rendering of something far richer. The true nature of reality might be hidden in dimensions we're not built to see, with consciousness itself as the elusive key to unlocking them. And if that's the case, the greatest discoveries in science won't be found in telescopes or particle colliders. They'll happen when we learn to see beyond the interface. Dark energy is the universe's most persistent riddle, a mysterious force accelerating the expansion of space, as if the cosmos itself is being pushed apart by invisible hands. Scientists have grappled with explanations, from quintessence fields to cosmological constants. But what if the answer isn't hidden in our four-dimensional world at all? Enter the five-dimensional Kaluza-Klein dark energy theory, a radical twist suggesting that dark energy might not be a thing in our universe. It could be the side effect of an entire dimension stretching just beyond our perception. Picture a balloon inflating. As it expands, dots drawn on its surface move apart, not because they're being pushed, but because the fabric they're embedded in is stretching. Now imagine that balloon has a hidden dimension one we can't see, but whose expansion tugs on our three-dimensional space like an unseen hand. That's the crux of this idea. While we measure dark energy as a mysterious pressure in our universe, its true source could be a fifth dimension slowly unfurling in ways we're only beginning to model. The equations trace back to Kaluza and Klein's pioneering work, but with a modern twist. Just as their fifth dimension unified gravity and electromagnetism a century ago, today's theorists propose it might also hold the key to cosmic acceleration. How does this differ from quintessence, the prevailing dark energy candidate? Quintessence imagines a dynamic energy field permeating space, its strength waxing or waning over time. But five-dimensional dark energy flips the script. Instead of a field within our universe, the acceleration could arise from the geometry of higher dimensional spacetime itself, a structural effect, not a substance. Think of the difference between wind pushing a sailboat quintessence and the ocean current carrying the entire sea Kaluza-Klein expansion. One is local, the other is foundational. Testing this isn't just theoretical gymnastics. Astronomers already have tools to probe the idea. Type Ia supernova, the same standard candles that first revealed cosmic acceleration, could hold subtle clues. If dark energy stems from a fifth dimension's expansion, the rate of acceleration might deviate from quintessence predictions in specific ways. Future observatories like the Vera-Rubin telescope will map billions of galaxies, searching for these anomalies in the universe's expansion history. Even gravitational wave detectors might spot ripples in spacetime carrying imprints of higher dimensional influence, like echoes from a hidden room. The implications are profound. If proven, five-dimensional dark energy wouldn't just solve a cosmic mystery, it would rewrite our understanding of reality's scaffolding. we'd be forced to accept that the universe's fate isn't dictated solely by what we see, but by dimensions we've yet to fully grasp. And that realization might be the first step towards something even grander, a unified map of all forces woven together by the hidden threads of higher dimensional space. Every particle in the universe hums with an invisible energy, a vibration so fundamental, it determines not just how particles move but what they are. At the heart of this quantum symphony lies a profound question. Could these vibrations extend beyond the three dimensions we know, resonating through hidden layers of reality? The idea of dimensional resonance suggests that particles might not just dance through space, they could be oscillating in extra dimensions, their frequencies dictated by geometries we can't perceive. And if that's true, it could unravel one of physics' deepest mysteries. Why do particles have the masses they do? Start with the Higgs field, that cosmic molasses filling the universe. When particles interact with it, they gain mass like wading through water. The more resistance they meet, the heavier they become. But here's the puzzle. Why does an electron weigh almost nothing compared to, say, a top quark? The Standard Model shrugs. It treats these masses as arbitrary inputs, but dimensional resonance offers a tantalizing alternative. Imagine extra dimensions curled up like tiny musical instruments, each with its own harmonic frequencies. A particle's mass might depend on how its quantum vibrations sync with these hidden geometries, like a guitar string's pitch changing with the tension and length of the neck. This isn't just poetic speculation. String theory already paints particles as vibrating strings, their notes corresponding to different properties. Extend that to higher dimensions and you get a richer harmonic landscape. Some vibrations might resonate powerfully with compactified dimensions, producing heavy particles, while others barely interact, remaining feather-light. Picture blowing across soda bottles filled to different levels. Each produces a distinct note based on its shape. Particles might work the same way, their masses tuned by the hidden dimensional architecture around them. Experimental hints are already stirring. The Large Hadron Collider hasn't just found the Higgs boson, it's measured its couplings to other particles with exquisite precision. Some deviations from predictions could point to extra-dimensional influences, like echoes of higher harmonics distorting a pure tone. Even more intriguing are rare particle decays, where unexpected patterns might betray hidden resonances. It's like listening for faint overtones in a song, clues to instruments playing just out of earshot. Critics argue this is speculative, and they're right, no smoking gun evidence yet. But the math is seductive. If dimensional resonance is real, it would mean the universe isn't just built on particles and forces, but on a hidden vibrational code. A cosmic music where mass, dimension, and vibration intertwine. And cracking that code wouldn't just explain why particles weigh what they do. It might reveal the universe's deepest secret, that matter itself is a shadow of dimensions we've yet to hear. At the smallest scales imaginable, where space-time itself frays into quantum foam, reality might not just get fuzzy, it could fundamentally change dimensions. Imagine zooming in on a digital photo until it dissolves into individual pixels. Now picture doing that to the universe itself. According to causal set theory and loop quantum gravity, space-time may not remain smooth and four-dimensional all the way down. Instead, at the Planck scale, a distance so tiny it makes atoms look like galaxies, the structure of existence could simplify into something shockingly flat. A two-dimensional framework where the very concepts of here and now break apart. Think of it like this: a woven blanket looks solid from afar, but up close, it's just threads crossing in two dimensions. Similarly, what we perceive as the rich, voluminous fabric of space-time might emerge from an underlying grid of interconnected points with no thickness at all. Causal set theory describes this foundation as a collection of discrete events linked by cause and effect relationships, a cosmic flowchart where dimensionality is an afterthought. Loop quantum gravity takes it further, proposing spacetime isn't continuous but pixelated, with tiny quantum loops forming a network so fine it only appears three-dimensional when you step back. Why would the universe flatten out at these scales? One clue comes from black hole thermodynamics. When calculating a black hole's entropy, physicists found it scales with the event horizon's area, not its volume, as if the information inside is somehow smeared across a 2D surface. This holographic principle suggests that at fundamental levels the universe might encode data more efficiently in fewer dimensions, like compressing a 3D movie onto a flat Blu-ray disc. The implications are staggering. If spacetime is 2D at its core, then our perception of depth might be an illusion woven by complexity, a cosmic magic trick where simple, flat interactions conspire to create the richness we experience. Even gravity, which bends our 4D spacetime, could be a side effect of these deeper, flatter relationships. It's like watching a shadow puppet show. The 3D shapes you see aren't really there, they're projections of 2D hands moving behind the scenes. Experiments to test this remain distant. Probing the Planck scale requires energies a quadrillion times beyond today's particle colliders. But subtle signatures might lurk in the cosmic microwave background or in the quantum jitters of spacetime itself. If we ever detect these fingerprints, it would mean reality isn't just stranger than we imagined, it's stranger than we can imagine, built on a canvas with fewer dimensions than the world it paints. What if our own biology, the very blueprint of life, holds whispers of hidden dimensions? From the spiraling elegance of DNA to the labyrinthine networks of the human brain, nature might be using mathematical shortcuts that bend beyond our familiar three-dimensional world. Scientists are uncovering eerie hints that biological systems don't just exist in dimensions, they might exploit them, folding and functioning in ways that defy conventional geometry. Take DNA under a microscope. It looks like an intricate staircase, the iconic double helix, but that's just the surface. Inside your cells, DNA doesn't float loosely. It coils, loops, and knots itself into fractal-like bundles so dense they pack 2 meters of genetic material into a nucleus 10,000 times smaller than a grain of salt. How researchers using algebraic topology, a branch of math that studies shapes in higher dimensional spaces, found something startling. The way DNA folds and interacts resembles mathematical operations in 4 or even 5 dimensions. Enzymes navigating these folds don't just slide along the helix like a train on tracks, they seem to jump between sections, as if teleporting through hidden geometric shortcuts. It's like watching someone solve a Rubik's Cube by flipping it through an invisible 4th dimension, rearranging colors in ways that seem impossible from our limited perspective. Then there's the brain, with its 86 billion neurons, each connecting to thousands of others. The human mind is the most complex structure we know of in the universe. Traditional 3D maps struggle to capture its true complexity. But when neuroscientists applied topology to brain scans, they discovered networks structured like hyperdimensional donuts or pretzel shapes that can't fully exist in our spatial reality without passing through themselves in higher dimensions. These structures might explain how the brain integrates information so seamlessly, blending memory, sensation, and thought into a unified experience. Imagine trying to untangle headphone cords in a drawer. The knots seem random until you lift them into the 3rd dimension, where the solution becomes obvious. The brain's knots might unravel similarly when viewed through a multidimensional lens. Even proteins, the workhorses of biology, play this game. To function, they must fold into precise shapes, sometimes in milliseconds. Chemists long assumed this was a trial-and-error process, like crumpling paper until it accidentally forms the right origami. But topology reveals a different story. Proteins might navigate a landscape of possible folds that resembles a high-dimensional funnel, with ridges and valleys guiding them to their correct form. Some researchers speculate these pathways could exist in abstract mathematical spaces, with each dimension representing a variable like temperature, pressure, or atomic charge. The implications are staggering. If biology taps into higher dimensional math, it could revolutionize medicine. Diseases like Alzheimer's, where proteins misfold catastrophically, might stem from errors in navigating these hidden geometric landscapes. Cancer cells, with their chaotic DNA packing, could be failing to maintain dimensional coherence, and brain disorders, they might reflect breakdowns in the hyperdimensional networks that let neurons communicate across layers of abstraction. Of course, skeptics argue this is just sophisticated metaphor, that nature isn't literally using extra dimensions, but our math happens to fit. Yet the predictive power is hard to ignore. Drugs designed with topological principles have already shown promise in targeting elusive proteins, and brain models incorporating higher dimensional math outperform traditional ones in simulating consciousness. Whether these dimensions are real or just useful fictions, one thing's clear: life doesn't play by the rules we thought it did. The deeper we probe, the more biology seems to dance in dimensions beyond our sight, a silent symphony of folding, knotting, and weaving that might just be the universe's most elegant cheat code. At the heart of Switzerland, buried beneath rolling hills and quiet farmland, the world's most powerful microscope hums with unimaginable energy. The Large Hadron Collider doesn't just smash protons together, it recreates conditions unseen since the universe's first trillionth of a second, searching for cracks in reality itself. Every collision is a potential doorway, a fleeting chance to catch hidden dimensions red-handed. But if extra dimensions exist, how would they reveal themselves in this subatomic maelstrom? The answer lies in two tantalizing anomalies: missing energy and microscopic black holes. Picture two cars colliding head-on at nearly the speed of light. When particles crash in the LHC, detectors capture the debris: photons, quarks, muons, painting a precise energy balance sheet. But if some energy consistently vanishes without explanation, it could mean particles are slipping into dimensions we can't see. Imagine tracking water flowing through a pipe, only to find a fraction mysteriously disappearing. You'd suspect a hidden leak. Similarly, if certain collisions show energy deficits matching higher dimensional models, it might mean gravitons or other particles are briefly tunneling into the bulk before decaying back into our brain. Then there's the ultimate smoking gun: microscopic black holes. In a universe with large extra dimensions, gravity's strength could spike at microscopic scales, making these bizarre objects possible at LHC energies. These wouldn't be the planet-swallowing monsters of sci-fi. They'd evaporate instantly via Hawking radiation, leaving behind a burst of characteristic particles like fingerprints on a cosmic crime scene. Detectors have searched for these flashes, but so far, silence. Does this mean extra dimensions don't exist? Not necessarily. Absence of evidence isn't evidence of absence, especially when we're probing realms a billion times smaller than an atom. The LHC might not be powerful enough to pierce through to certain dimensional scales, like trying to hear a whisper across a football field with a stethoscope. Future colliders, like the proposed Future Circular Collider with 7 times the energy, could push these boundaries further. Another possibility: we've been looking for the wrong signatures. Higher dimensions might manifest not as dramatic energy gaps or black holes, but as subtle deviations in particle behavior, slight excesses of muons or unexpected angular distributions in collision debris. Like detectives sifting through circumstantial evidence, physicists now comb petabytes of LHC data for these statistical whispers. The stakes couldn't be higher. A single verified anomaly could rewrite the textbooks, proving we're not just inhabitants of space-time, we're surrounded by invisible folds, waiting to be pulled into the light. Until then, the collider's beams keep circling, each pulse a question hurled into the dark. Are we alone in this cosmic house, or are there doors we haven't found the handles to yet? When the Event Horizon Telescope unveiled humanity's first image of a black hole's shadow in 2019, that fiery ring around the abyss of M87's core, it wasn't just a triumph of astrophysics. It was a potential window into dimensions we've never seen. That haunting silhouette created by light bending around the black hole's event horizon might hide subtle distortions that betray the presence of hidden dimensions. According to recent studies, if our universe has extra spatial dimensions beyond the familiar three, their gravitational influence could warp the shadow's shape in ways that defy Einstein's predictions. Think of it like a fingerprint on glass. Under normal light, a window appears flawless, but tilted just right and smudges emerge, traces of an unseen touch. Similarly, black hole shadows in a 4 or 5-dimensional universe wouldn't match the near-perfect circles predicted by classical general relativity. Higher dimensional gravity would bend light differently, possibly flattening one side of the shadow or creating faint secondary rings, like ripples from a pebble dropped into a pond with invisible layers beneath. The Event Horizon Telescope's next-generation upgrades with even sharper resolution could spot these anomalies. The math behind this is staggering. Simulations of black holes in higher dimensional spaces like those modeled by physicists like Pau Figueres and Marcus Cunish show shadows that resemble squashed versions of their 3-dimensional counterparts. In some scenarios, the shadow might develop edges sharper than expected, as if part of the light is vanishing into another dimension. Other models predict faint, ghostly echoes around the primary ring light that's traveled through warped space-time geometries before looping back into our view. Critics argue these deviations could be chalked up to more mundane factors, like the black hole's spin or interstellar dust. But proponents counter that certain signatures like asymmetries that can't be explained by spin alone could be the smoking gun. Future observations of Sagittarius A star, the supermassive black hole at our galaxy's center, might hold the key. Unlike M87, which we see nearly face-on, Sagittarius A star's tilted angle could amplify dimensional distortions, making them easier to spot. The stakes are cosmic. If black hole shadows betray extra dimensions, it wouldn't just confirm string theory or Brane worlds. It would mean these hidden realms sculpt the most extreme objects in existence. Every black hole might be a dimensional prism, bending not just light, but the very fabric of reality around it. And the next time the Event Horizon Telescope snaps a photo, we might not just be seeing a black hole. We could be glimpsing the edges of a universe far larger and far stranger than we ever imagined. What if the universe isn't just hiding extra dimensions? What if it's running on them? Nick Bostrom's infamous simulation hypothesis suggests our reality might be an artificial construct, an advanced computational model built by some superintelligent civilization. But here's the twist. If we're living in a simulation, the architects wouldn't need to exist in our 3-dimensional framework at all. They could be operating from higher dimensions, manipulating our world like programmers tweaking code from outside the system. Think of it like a video game designer working in 3 dimensions while the characters on screen only perceive 2. To those digital avatars, the designer is an incomprehensible entity able to pause their world, alter its physics, or peer into any corner instantly. Now scale that up. A civilization mastering 5 or 6 dimensions could treat our universe as a sandbox, with cosmic constants like gravity and the speed of light merely adjustable parameters in their grand experiment. Even the Big Bang might just be a boot-up sequence, but is this testable science or just philosophical speculation? Some researchers argue that if our universe is a simulation running on higher dimensional hardware, there could be glitches, tiny imperfections in the fabric of reality where the underlying code shows through. Physicists have proposed hunting for these anomalies in the cosmic microwave background, the universe's oldest light. Unexplained pixel-like patterns or unnatural geometric symmetries might hint at a programmed structure. Others suggest looking for mathematical constraints like hard limits on energy or spatial resolution that could betray a computational framework. Then there's the dimensionality loophole. If simulation architects exist in higher dimensions, their actions might leave gravitational echoes in our universe. Strange, unexplained gravitational waves or particles appearing to vanish into thin air could signal interference from outside our dimensional plane. Projects like the Laser Interferometer Gravitational Wave Observatory LIGO could one day catch these whispers of higher dimensional tinkering. Critics, of course, dismiss this as unfalsifiable fantasy. How do you prove something exists outside reality when all your tools are bound by that reality's rules? But proponents counter that the simulation argument isn't about proof, it's about probability. Bostrom's original trilemma suggests one of three things must be true. Civilizations never reach post-human capabilities. They choose not to run ancestor simulations, or we're almost certainly living in one. Hidden dimensions add a fourth possibility. They're running simulations from vantage points we can't access, like ants trying to comprehend cloud computing. The chilling beauty of this idea is its double-edged nature. If higher dimensional simulators exist, they might not just be observing, they could be optimizing, pruning branches of reality that don't serve their purpose. Are we the main simulation or a discarded prototype? Are black holes garbage collection mechanisms for failed universes? The questions spiral into existential vertigo. Yet for all its drama, the simulation hypothesis forces us to confront a deeper truth. Whether we're in a program or not, the nature of reality is far stranger than we assume. Dimensions might not just be hidden, they could be the scaffolding of someone else's experiment. And if that's the case, the greatest scientific discovery wouldn't be finding them. It would be realizing we were never the ones in control. Cosmic strings are like scars left over from the universe's fiery infancy, remnants of a time when reality itself was still cooling into its current form. Picture the early cosmos as a vast pot of water just beginning to freeze. As ice crystals form, imperfections emerge, tiny cracks and boundaries where the structure doesn't quite align. Now imagine that happening to space-time itself during the universe's first moments, when fundamental forces were settling into place. These misalignments could have frozen into one-dimensional defects, cosmic strings threading through existence like invisible wires. Some theorists suggest these strings aren't just relics. They could be bridges between dimensions, remnants of higher dimensional physics that got tangled in our three-dimensional world. What makes cosmic strings so strange is their sheer density. A single string thinner than a proton could stretch across billions of light years, weighing as much as a mountain range crammed into every mile. If one were to pass through Earth, it wouldn't slice through us like a knife. Instead, its immense gravity would warp space around it, creating bizarre distortions. Clocks might tick at different rates on opposite sides of the string, and light could bend around it like a funhouse mirror. Astronomers have searched for these telltale warps in distant galaxies, looking for double images of the same quasar split by a string's gravitational lens. So far, no definitive sightings, but the hunt continues. Here's where it gets even wilder. Some models propose that cosmic strings could be direct evidence of hidden dimensions. In certain theories, like brane inflation, strings aren't just flaws in our universe's structure, they're like loose threads dangling from a higher dimensional tapestry, tethered to other branes or dimensions we can't see. These strings wouldn't just warp space, they might vibrate in ways that leak energy into other dimensions, leaving faint gravitational ripples or even influencing galaxy rotation in unexpected ways. Observations of some galaxies show stars orbiting too fast at their edges, a discrepancy usually blamed on dark matter. But what if some of that motion is due to unseen cosmic strings, their gravitational pull subtly tweaking stellar orbits from behind the scenes? The math behind this is as elegant as it is mind-bending. String theorists like Alexander Vilenkin have shown how these defects could naturally arise when higher dimensional symmetries break during the universe's early expansion. It's like stretching a rubber sheet covered in ink. As it expands, cracks form in predictable patterns, revealing hidden structures beneath. If cosmic strings do connect to extra dimensions, detecting their gravitational signatures could give us indirect proof of realms beyond our perception. Future observatories like LISA, the space-based gravitational wave detector, might pick up the faint hum of a string's vibrations ripples not just through space, but through dimensions we've yet to map. For now, cosmic strings remain one of cosmology's most tantalizing what-ifs. They're reminders that the universe's grandest mysteries might not be written in distant stars or quantum particles, but in the very fabric of space-time itself, stitched together with threads that could lead us straight to the doorsteps of hidden dimensions. And if we ever find one, it won't just be a discovery. It'll be a message from the early universe, whispering clues about the true shape of reality. Imagine a symphony where every instrument plays by different rules. The violin follows one conductor, the trumpet another, and the drums ignore both entirely. That's the chaotic state of modern physics, with quantum mechanics and general relativity refusing to harmonize. But what if the discord isn't due to flawed theories, but because we've been missing most of the orchestra? Enter M-theory, the boldest attempt yet to unify all forces of nature by proposing reality isn't just 4-dimensional, but 11-dimensional, with 7 hidden dimensions orchestrating the cosmos behind the scenes. M-theory emerged from a stunning realization in the 1990s. 5 competing string theories, each with their own equations and dimensions, were secretly facets of a single, deeper framework. Like discovering that electricity and magnetism weren't separate phenomena but expressions of electromagnetism, physicists found that these string theories were different angles of an 11-dimensional structure we now call M-theory. The M stands for mystery, magic, or membrane. No one's quite sure, but its implications are crystal clear. The universe might be a vibrating, multidimensional entity where all forces arise from the same fundamental strings. Here's where compactification plays soloist. Those 7 extra dimensions don't sprawl endlessly like our familiar 3. They're curled into shapes so tiny they're imperceptible to our senses. Picture a garden hose seen from a distance. It looks like a one-dimensional line, but up close, you realize it's a cylinder with a circular second dimension wrapped around it. M-theory suggests something similar, but with geometries far more complex than simple loops. These hidden dimensions could be twisted into Calabi-Yau manifolds, intricate 6-dimensional shapes that determine how strings vibrate. Each vibration mode corresponds to a different particle or force, like musical notes emerging from the geometry of an instrument. Gravity's puzzling weakness suddenly makes sense in this framework. While electromagnetism and nuclear forces are confined to our 4-dimensional brain, gravity could be seeping into the full 11-dimensional space, diluting its strength like perfume dispersing through a mansion. This leakage might explain why gravity is 10 to the power of 39 times feebler than the other forces. It's not weak, just spread thin across dimensions we can't perceive. Yet M-theory remains tantalizingly incomplete. Unlike string theory, which has well-defined equations, M-theory's full mathematical formulation is still a work in progress. It's like having sheet music for individual instruments but no score for the entire symphony. Some researchers suspect M-theory requires entirely new mathematical tools, perhaps something beyond our current understanding of geometry or algebra, to fully describe how membranes, strings, and dimensions interact. The stakes couldn't be higher. If M-theory holds, it wouldn't just unify physics, it would redefine reality. Particles, forces, even the fabric of space-time would be vibrations of multidimensional membranes, dancing to a tune written in 11 dimensions. We might finally answer why the universe has the precise mix of forces it does, or why constants like the speed of light have their exact values, and hidden in those 7 curled-up dimensions could be the greatest secret of all. The universe isn't just stranger than we imagined. It's stranger than we can imagine, at least for now. Long before physicists scribbled equations about brains and bulk, our ancestors were spinning tales of hidden worlds, stairways to heaven, layered realms, and divine ladders stretching beyond the sky. Take Jacob's ladder from the book of Genesis, where angels ascend and descend between earth and the heavens. The description isn't just poetic, it's eerily reminiscent of a higher dimensional bridge linking parallel planes of existence. Or consider the Hindu concept of lokas, 14 distinct realms stacked like layers of a cosmic onion, each with its own laws and beings. These aren't just flights of fancy. They could be humanity's earliest intuitions about multidimensional reality encoded in allegory. Think of myths as ancient thought experiments. When the Norse spoke of Yggdrasil, the world tree connecting 9 realms through its roots and branches, they might have been grappling with the same questions that keep string theorists awake at night. How do separate realities interact? What unseen structures bind them? The tree's axis piercing through worlds mirrors modern diagrams of compactified dimensions, tiny, curled-up spaces that tether our universe to others. Even Plato's allegory of the cave, where prisoners mistake shadows for reality, feels like a prescient metaphor for beings trapped in a 3-dimensional slice of a richer cosmos. The parallels grow stranger when you examine the details. In Buddhist cosmology, Indra's net describes a vast web where every jewel reflects all others, a striking analog for holographic theory, where every part of the universe contains information about the whole. The Dogon people of Mali, who knew of Sirius B, a white dwarf invisible to the naked eye centuries before telescopes, spoke of ancestral spirits navigating threads between stars. Could these threads be wormholes or dimensional filaments? Skeptics dismiss such connections as coincidence, but the consistency across cultures is hard to ignore. Modern physics offers a provocative lens to reinterpret these stories. When string theorists talk about Calabi-Yau manifolds, those 6-dimensional shapes curling unseen beneath space-time, they're describing geometries that would have been unimaginable to ancient scribes. Yet, the Mayan Popol Vuh speaks of roads through the sky, used by gods to traverse hidden realms, while Aboriginal Dreamtime stories describe song lines crisscrossing the land in patterns that map both physical and spiritual dimensions. These narratives don't use terms like quantum entanglement or brain collisions, but the underlying intuition that reality has layers we can't normally access resonates across millennia. What if these myths aren't just metaphors, but fragmented reports of actual experiences? Shamans in Siberia and the Amazon speak of ayahuasca or mushroom-induced visions where they travel to alternate worlds, encountering beings who teach them about the fabric of existence. In controlled studies, psychedelics like DMT reliably induce encounters with entities and perceptions of hyperdimensional spaces, geometric realms that users insist feel more real than waking life. Could these substances temporarily unshackle the brain from its 3-dimensional constraints, allowing glimpses into the bulk? It's a radical idea, but one that bridges anthropology and theoretical physics in ways we're only beginning to explore. The most tantalizing possibility is that ancient cultures knew things we're just rediscovering, not through equations, but through direct experience or lost wisdom. The Egyptian Book of the Dead describes the soul navigating Juwat, a realm with gates governed by precise geometry, while Taoist texts reference Qigong practices to manipulate subtle energies in higher dimensional bodies. Even Dante's Divine Comedy, with its 9 concentric circles of hell, mirrors modern multiverse models where gravity warps space into nested layers. Critics argue that imposing modern physics onto mythology is retroactive pattern matching seeing faces in clouds. But the counter is equally compelling. When disparate cultures, separated by continents and centuries, describe similar structures independently, it suggests a shared intuition about reality's hidden architecture. Perhaps the next breakthrough in understanding dimensions won't come from a super collider, but from decoding the collective subconscious. the stories we've been telling ourselves all along about the universe's secret doors. After all, the line between myth and science has always been thinner than we think. Every legend about climbing to heaven might just be a different dialect of the same truth. We're surrounded by dimensions waiting to be seen. String theory's tangled equations hit a snag when physicists realized they required 10 dimensions to stay mathematically consistent, a headache for anyone trying to map reality's blueprints. But what if there was a way to streamline the chaos? Enter 10-dimensional supergravity, a revolutionary framework that pares string theory's complexity down to something almost elegant. Unlike the labyrinthine equations of full string theory, supergravity models treat particles as fields rather than vibrating strings, simplifying calculations while preserving the dream of unifying all forces. Picture trying to navigate a city with 10 twisting roads. Supergravity hands you a subway map, highlighting only the most essential connections. At its core, this framework merges Einstein's general relativity with supersymmetry, creating a universe where gravity isn't an outsider but a natural player in the quantum realm. The star of the show, the graviton, a hypothetical particle that would carry gravitational force just as photons carry light. In 10D supergravity, gravitons emerge effortlessly from the math, massless, chargeless, and spinning with twice the energy of photons. They're the glue that could bind quantum mechanics and gravity, but there's a catch. These models predict too many gravitons, along with a zoo of other particles that don't match our observed universe. It's like baking a cake with a perfect rise, only to find the recipe also demands ingredients nobody's ever seen. The real magic lies in how supergravity handles those extra dimensions. Instead of letting them sprawl unpredictably, it rolls them into tight, symmetrical shapes like cosmic origami. One version, called Type AB supergravity, treats dimensions as mirrors of one another, folding space into patterns that could explain why gravity feels weak in our 3D world. Another, 11D supergravity, yes, it sneaks in an extra dimension, hints at a deeper structure that might underlie all string theories. But here's the rub. These models still can't explain why we're stuck with exactly 4 visible dimensions or how the others stay hidden. The math sparkles with elegance, yet reality refuses to cooperate. Critics argue that supergravity's simplicity comes at a cost. Without the full machinery of string theory, it struggles to account for quantum effects at ultra-small scales like those near black holes. It's akin to using Newton's laws to describe planetary motion, brilliant until you reach relativistic speeds. Yet even incomplete, these models have reshaped physics. They've inspired Brane World scenarios, hinted at dark matter's hidden signatures, and given mathematicians new tools to explore the geometry of spacetime. The lesson, sometimes looking for answers in higher dimensions, isn't about finding finality. It's about discovering which questions are worth asking next. And if history's any guide, the gaps in supergravity's logic might be the very cracks where a deeper truth slips through. Quantum mechanics has always been the wild frontier of physics, where particles exist as probability clouds, spinning in multiple states at once until observed. But what if the moment of observation, that mysterious collapse of the wave function, isn't just a quirk of measurement here in our dimensions? What if it's a signal, a shadow of something far stranger happening in the hidden layers of reality? One audacious idea suggests that quantum decoherence, the process that snaps particles from maybe to definitely, might be the result of interactions with dimensions beyond our own. Picture Schrödinger's infamous cat, both alive and dead in its box until someone peeks inside. Traditional interpretations scramble to explain this paradox. The many worlds theory says every possibility branches into parallel universes somewhere. The cat lives, elsewhere it doesn't. Pilot wave theory posits unseen forces guiding particles like tiny marionettes. But the dimensional decoherence theory offers a radical third path. What if the act of observation isn't creating new realities or revealing hidden variables, but instead tugs on invisible threads woven through extra dimensions? Imagine tossing a pebble into a pond. The ripples spread across the surface, but also push downward into depths you can't see. Similarly, when we measure a quantum system, our instruments might be disturbing higher dimensional fields, forcing particles to choose a state in our familiar three-dimensional slice. The math behind this is as elegant as it is mind-bending. In certain Brane World models, particles aren't just confined to our brain. Their wave functions could bleed into the bulk, the higher dimensional space surrounding us. Decoherence would then occur when these extended wave functions interact with structures in the bulk, like vibrations dampening when they hit a wall. It's akin to how a guitar string's harmonics change if you press it against a fret. Our reality might just be one note in a multidimensional chord. Critics argue this seems like an elaborate excuse to avoid the weirdness of quantum mechanics. After all, invoking extra dimensions to explain wave function collapse could be seen as replacing one mystery with another. But proponents counter with a compelling point. This framework naturally explains why quantum systems stay coherent in isolation, no bulk interactions, but collapse when measured. Our devices anchor them to our brain. It also dovetails with the holographic principle, the idea that our 3D universe is a projection of information stored on a 2D boundary. If decoherence happens offstage in higher dimensions, it would neatly fit the hologram metaphor. The stakes are high. If dimensional decoherence is real, it wouldn't just rewrite quantum theory. It would offer a tangible bridge between the quantum and cosmic scales. Black holes, for instance, might decohere matter not by destroying information, but by shunting it into the bulk. Even entanglement, that spooky connection between particles, could be a higher dimensional handshake, with particles linked through shortcuts in the geometry of hidden space. So next time you hear about a quantum experiment, photons acting as waves or particles depending on how they're observed, consider this wild possibility. The answer might not lie in our world at all, but in the silent, unseen dimensions that hum just beneath the surface of reality, pulling the strings of the quantum dance we're only beginning to witness. Most theories tuck extra dimensions away at microscopic scales, but what if one of them is vast, stretching light years across yet remaining invisible to our eyes? This is the provocative idea behind the dark dimension theory, where a single, large extra dimension serves as the hidden playground for dark matter. Unlike the ad arcani Haim Dimopoulos Divale model, which proposes multiple millimeter-sized dimensions to explain gravity's weakness, the dark dimension is unique. It's just big enough to house dark matter particles while staying just out of reach of our detectors. Think of it this way. If our three-dimensional universe is a flat sheet of paper, the dark dimension would be like a parallel sheet hovering millimeters above it, too close to see from a distance but utterly separate. Dark matter particles could move freely between these sheets, drifting in and out of our dimension like ghosts passing through walls. This setup elegantly explains why dark matter barely interacts with normal matter. It's not that the particles are inherently shy. They're simply spending most of their time elsewhere in a dimension adjacent to ours. Gravity, the only force known to cross dimensional boundaries, would still tether dark matter to our universe, creating the gravitational scaffolding that holds galaxies together. But here's the twist: the dark dimension wouldn't dilute gravity like ad model. Instead, it would warp the way dark matter clusters, leaving subtle fingerprints in the cosmos. For instance, simulations show that dark matter in a bulk dimension would form smoother, more diffuse halos around galaxies closer to what we observe than traditional cold dark matter predictions. How could we ever detect such a hidden realm? The key might lie in high-energy particle collisions. If dark matter particles occasionally leak into our dimension, they could leave traces in experiments like the Large Hadron Collider, missing energy events that defy standard physics. Even more intriguing are gravitational wave observatories. Ripples in space-time from merging black holes might carry imprints of the dark dimension's geometry, like echoes bouncing off a hidden wall. The dark dimension isn't just another abstract idea, it's a testable bridge between the known and the unknown. If proven, it would mean we're not just surrounded by dark matter, we're sharing our universe with an entire dimension we've yet to step into. And that changes everything. When black holes collide, they don't just send ripples through space, they might shake the very foundations of reality. Gravitational wave detectors like LIGO have already revolutionized astronomy by capturing these space-time tremors, but hidden within those signals could be something even more extraordinary, faint echoes betraying the presence of extra dimensions. The idea hinges on a simple but profound question: when two black holes spiral toward cataclysmic merger, where does some of their energy go? According to recent studies, a fraction might be leaking into dimensions we can't see, leaving telltale distortions in the gravitational waves we detect. Picture dropping a pebble into a still pond. The ripples spread outward in clean, concentric circles unless there's a hidden obstacle beneath the surface. Then you'd see faint secondary ripples, echoes of the initial splash interacting with something unseen. Similarly, when black holes merge in a universe with extra dimensions, their gravitational waves wouldn't just propagate through our familiar three-dimensional space. Some of the energy would scatter into the bulk, the higher dimensional realm predicted by string theory and Brane World models. These scattered waves could then reflect back into our dimension, creating subtle echoes in the signal arriving milliseconds after the main event. It's as if the merger is happening in a cathedral rather than an empty field, with the architecture of hidden dimensions adding reverberations to the primary blast. The hunt for these echoes is already underway. In 2017, a team analyzing LIGO first black hole merger data reported unusual post-merger oscillations, small bumps in the signal that didn't match standard relativity predictions. Subsequent papers showed these anomalies could align with models where gravity leaks into a fourth spatial dimension during the merger's violent finale. The key signature, a series of dampened, evenly spaced pulses following the main gravitational wave, like a bell's lingering ring after the initial strike. Not all researchers are convinced. Some argue noise or instrument artifacts could mimic these patterns, but the statistical analyses keep fueling debate. What makes this approach so powerful is its specificity. Unlike particle colliders that blast matter to uncover hidden dimensions, gravitational waves offer a pristine probe. They're pure vibrations of spacetime itself, undisturbed by electromagnetic interactions that could muddy the signal. Future detectors like the space-based LISA Observatory or next-generation ground arrays will have the sensitivity to spot even fainter echoes, potentially mapping the shape of extra dimensions through their acoustic fingerprints. Imagine astronomers not just hearing the song of colliding black holes, but detecting the hidden concert hall those notes are echoing through. The implications stretch far beyond proving theoretical models. If LIGO or its successors confirm dimensional echoes, it would mean we're not just detecting cosmic events, we're eavesdropping on the architecture of reality itself. Every black hole merger would become a dimensional sonar pulse, revealing structures smaller than an atom yet vast enough to alter the universe's gravitational soundtrack. And somewhere in those faint after ripples might lie answers to questions we've barely learned to ask. From the infinitesimal twists of Calabi-Yau manifolds to the vast stretches of warped brains, each theory we've explored peels back another layer of reality's deepest secrets. Some suggest gravity's weakness is just a cosmic illusion, an echo of forces spilling into unseen dimensions. Others propose that black holes aren't endpoints but gateways, their shadows flickering with hints of higher dimensional geometry. And then there's the haunting possibility that consciousness itself might be navigating a reality far richer than the three dimensions we perceive. What's astonishing isn't just the diversity of these ideas, it's how they converge like rays of light through a prism. String theories, vibrating filaments, the holographic principles, cosmic projections, and the dark dimensions' hidden playground for matter all point to a universe far grander, weirder, and more interconnected than we ever imagined. Even the contradictions are thrilling. Does time flow forward because of dimensional geometry, or is its arrow an emergent illusion? Are we alone in this cosmic house, or are parallel brains brushing against ours in the void? The beauty of these theories lies in their audacity. They don't just answer questions, they redefine what questions are worth asking. And while we might not have proof yet, the hunt itself is transformative. Every unexplained gravitational ripple, every anomalous particle collision, every glimmer in the cosmic microwave background could be a breadcrumb trail leading to dimensions beyond our senses. So, which theory reshaped your understanding of reality? Was it the holographic universe's suggestion that everything you see is a projection, or the chilling elegance of cosmic strings threading through space-time like seams in a hidden tapestry? Drop your mind-blown reactions in the comments, and if you're hungry for more cosmic mysteries, hit subscribe. The universe's greatest secrets are still out there, waiting in the dimensions we've yet to explore.